Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So now, some of you asked about the process of radiation. The process of radiation, how is the field coming out from the antenna? So, in order to understand that, we'll consider the Hertz dipole, which is the most fundamental uh, antenna, and it's the building block for any kind of antennas. So, we'll try to analyze Hertz dipole so that we understand the process of radiation from the Hertz dipoles, and from there we can infer the process of radiation for other antennas also. So just before that, let us try to analyze Hertz dipole in the near field. So we have already done the derivation for electric fields and magnetic field produced by Hertz dipole, infinitesimally current carrying element. This is the magnetic field for Hertz dipole in the near field. So NF means near field. Magnetic field in the near field has only 5 components, and this is the expression for the magnetic field. So now what we want to see is that in the near field, the expression for the magnetic field is very similar to that of the expression we obtain using the Biot-Savart's law. So you know that Biot-Savart's law is used for finding the magnetic field for magnetostatics. So if you want to find magnetic field B, magnetic flux density B, using Biot-Savart's law, BSL means Biot-Savart's law, how do you do it? That's a standard expression you have, mu 0 I 0 del cross R by 4 pi R squared. This is the expression you have for the magnetic field due to a current carrying element dl, and in our case we have considered the current carrying element is along the z-axis. So if the current carrying element is along the z-axis, this vector dl vector will become just dl z hat, because the direction of current flow is along the z direction. And we know that we want to analyze the magnetic field and electric field for the antennas and the spherical coordinates. So in that case, I don't want any Cartesian coordinate unit vectors here, so I'll replace this Cartesian coordinate unit vector z hat, and we have already done this when we analyze the Hertz dipole. Z hat can be expressed as cosine theta r hat minus sine theta theta hat. So z hat will have two components, along the one along the radial direction, one along the theta direction. So when I do cross product of unit vector along the z-axis and the radial direction, I will simply get sine theta phi hat. So we can find out the magnetic flux density using the Biot-Savart's law for a small current carrying element which is directed along the z-axis simply as this: mu 0 I 0 del sine theta phi hat divided by 4 pi r square. But now we are interested in the magnetic field intensity. So magnetic flux density is related to the magnetic field intensity as B is equal to mu h. So I can find out magnetic field intensity using the Biot-Savart's law will be I naught del sine theta phi hat divided by 4 pi r squares. So going back to the expression you have for the H pi in the near field of a Hertz dipole, this was the expression. So if you compare these two equations, the only difference is the exponential plus j omega t and exponential minus j beta r term you have for the near field magnetic field of a Hertz dipole. But from the Biot-Savart's law, for any current carrying element along position along the z-axis, this is the expression you have for the magnetic field intensity. So now, but this Biot-Savart's law is actually applicable for magnetostatics. So let us assume that the field is for the case omega is tending to 0. So magnetostatics means electric field, the magnetic field would be that in the magnetostatics, you know that the current will not be time varying, current will become DC current, not AC current. So in that case, the frequency will be tending to 0. So omega will be tending to 0, and you know beta is omega square root of mu epsilon. Beta will be also tending to 0. In that case, this term here, exponential plus j omega t exponential minus j beta r, omega is tending to 0 and beta is tending to 0, so these terms will become 1. So simply what we have is exactly the same expression for the near field magnetic field of Hertz dipole with that of the magnetic field which has been obtained using the Biot-Savart law for magnetostatics. So this is one surprising result, and similarly we'll also observe another relation for the electric field. No? If you consider electric field, near field electric field of Earth dipole is having two components, one along the radial direction, one along the theta direction. We have already derived this. So for the near field component, it will be having variation with respect to r as 1 by r cube here, 1 by r cube here. So now what we can do is we can also find the potential due to an electric dipole. So let's say you have a positive charge q and you have a negative charge. It will form an electric dipole. Distance between them is, let's say, dl. So let's say you have a positive charge plus q and you have a negative charge plus minus q, and distance between them is dl. Then you can find out the electric potential due to a electric dipole as simply q by 4 pi epsilon 0 1 by r1 minus 1 by r2, where r1 and r2 are the distance of the observation point from the positive charge plus q and negative charge minus q. So now this you can simplify as r2 minus r1 by r1 r2, and if you are observing this electric potential at a little bit far away distance from the dipole, and any distance would be, you move little bit further away from the dipole, the distance, any further distance from the dipole, since the size of the dipole is very small, dl, which is of infinitesimally small size dl, in that case any distance you move little bit further from the dipole, it will be very far away from the source. So in that case your r1 and r2 will become r, and you can also find out that r2 minus r1 is equal to dl cos theta. So cos theta is the angle. See, basically we are keeping plus q and minus q at you are keeping plus q at plus dl by 2, and you are keeping minus q at minus dl by 2 along the z axis. So you are keeping plus q charge and minus q charge along the z axis. The location of plus q charge is 0, 0, dl by 2, and location for the minus q charge is 0, 0, minus dl by 2, and the angle, the position vector r from the origin to the observation point. So basically r is the distance of the origin to the observation point, and r1 is the distance of the plus q charge to the observation point, and r2 is the distance of the minus q charge to the observation point, and the angle theta is the angle radiation vector, what is that, radial distance r max with the z axis. So in that case you can find out r2 minus r1 is dl cos theta. We have done this similar kind of derivation when you consider antenna array also, Hertz dipole also in the far field, but here we are not considering far field since the size of the antenna is very small. Any distance you move little bit farther, it's a very far away distance from the dipole. So you can find out the voltage for this dipole is q by 4 pi epsilon 0 dl cos theta by r square. So from the voltage, if you want to find the electric field of the dipole, you take the negative gradient of the potential of the dipole, and we are doing it in the spherical coordinate. So you will have del by del r hat, del by del theta r theta hat. This is the scale factor 2, this is scale factor 1 is 1, scale factor 2 is r, scale factor 3 is r sin theta. So del by del phi 1 by r sin theta. So you do the partial derivatives, all these partial derivatives here of the electric potential for the dipole, then finally what you're getting is this. So now finally the electric field for the dipole is like this: 2q dl cos theta by 4 pi epsilon 0 r cube r hat plus q dl sin theta by 4 pi epsilon 0 r cube theta hat. So electric field for the dipole is having radial component and theta component, and if you compare the electric field of a Hertz dipole in the near field, you will observe that these two expressions are exactly same. One point to be noted here is that you have exponential I0 exponential j omega t divided by j omega for time harmonic fields will become q. When you integrate I0 exponential j omega t dt, what do you get? Q. Because when you integrate current, you get the charge. So if you replace this I0 exponential j omega t by j omega by q, and you know that if you consider frequency is tending to 0, then beta is also tending 0. This term will become 1. Exponential minus j beta r will become 1. So finally, if you compare these two equations, you are getting the near field of the Hertz dipole is exactly same as that of the electric field produced by a dipole, electric dipole. So this is also one very good observation you can make, and from this observation what you can do is that you can assume that in the near field of the Hertz dipole, the Hertz dipole is behaving like a dipole, electric dipole, and you can find out the process of radiation heuristically. This is not exact, but I mean you can understand how is the field radiated from a Hertz dipole. If you know how the field is radiated from a Hertz dipole, you can easily do it for other antennas, because Hertz dipole is the basic building block for any kind of antennas. So let us look at this diagram carefully. See, basically we have a Hertz dipole, and from the previous derivation we have here in the near field, the Hertz dipole has the same electric field as that of an electric dipole. So we'll assume that Hertz dipole is basically an electric dipole, and electric dipole is basically you have a plus charge here, you have a minus charge here. This is length of the dipole. So you have a plus charge at the top and minus charge at the bottom, and distance between them is dl. So this is the one model you can assume for the Hertz dipole, and it is possible from this relation we have derived here in the electric field and near field of the Hertz dipole is equivalent to electric field of a electric dipole. So that from that derivation I can assume that Hertz dipole is a electric dipole with plus charge and minus charge, and the dipole distance between the two charges of the dipole is dl. So now this is the model we are going to use and find out how field is radiated from the Hertz dipole. So now at time t is equal to 0, look at this graph here. You know that current distribution of a Hertz dipole, current will increase, then again decrease with respect to time. So we'll divide this current distribution of the Hertz dipole into 4 parts: part A, part B, part C, and part D, and we'll try to see this is the current, I with respect to time. So how this will radiate fields, that's what we're going to see. So now for the part A, when time t is equal to 0, what was the current? Current was 0. So in that case, the model of the Hertz dipole is a plus charge at the end of the Hertz dipole and minus charge at the end of the Hertz dipole. So now at the end there is no current flow. So at the end, whenever you are at the end of the Hertz dipole, there won't be any current flow because conductor is ending there. So in that case, current is 0 when the plus charge is here, minus charge is here, and they are at the distance dl. So now acceleration would be maximum, because from there current will again come back. See, basically we are assuming that this plus charge and minus charge are oscillating. It goes to the end, then comes here, then goes to the end and comes here. It's oscillating. So from there field is getting radiated. That's the model we are going to consider. At the time t is equal to 0, the current is 0 and the maximum acceleration will be there for this plus charge, because there will be attraction between this plus charge and minus charge. So they will try to move in these directions. So now at time t is equal to t by 8, capital T is the time period we have here. So at time t is equal to capital T by 8. So at this position now this charge start moving. Both the charges are moving. This charge is moving towards this direction, negative charge, positive charge is moving towards this direction. So now positive charge is moving towards this direction, means current is flowing in this direction. Negative charge is moving in this direction, current is also flowing in this direction. So overall current is flowing like this. And you know that this is the fill line of a plus charge and minus charge. So fill is starting from the plus charge and it's ending at the negative charge. So that fill line, when this charge start moving, that fill line will become like this. So as soon as this charge come here, this charge comes here, fill lines will change like this. So now at time t is equal to capital T by 4. So we are at this location now. So at time t is equal to capital T by 4, this charge and this charge, they are almost crossing each other. They are almost crossing each other. At this point you will have the maximum current. So you will have the maximum current because the charges are very near now. So maximum current will be there, they are flowing. So the current you will have maximum here. This is this point here. Time t is equal to T by 4. Then after that the charge will cross each other. So this positive charge will keep on going towards this direction and the negative charge will keep on going in this direction. So now negative charge is going in this direction, current is still flowing in this direction, and positive charge is moving in this direction, current is still flowing. But see here, one observation you can make is when this plus charge and minus charge cross each other, the fill lines will cut out. See, the fill lines will cut out at one time when t is equal to T by 4, capital T by 4. So at that point, plus charge and minus charge, they will neutralize. Plus charge and minus charge, when they reach at the same point, the fill will become 0 because current is 0. And electric plus point and minus point, they are at the same location. At that point the fill will become null here. So fill will become null, then this fill will detach from the Hertz dipole, then it comes out. So that fill is what we have here, this portion which has detached from the Hertz dipole. But the process, the harmonic motion of the charge keeps on continuing. It's not one time process. So this negative charge will keep moving towards this direction, positive charge will keep moving towards this direction. So in that case, so now current is still flowing in this direction, but then charge now positive is here, negative is here. So the fill lines in this case will be starting from here and it will be ending here. Again at time t is equal to 3t by 8, we are here. So at time t is equal to t by 2 at this location, this charge will keep moving towards the end and this charge will keep moving towards the end. We have this fill line here. This is the charge at the bottom, plus charge at the bottom and minus charge at the top. So fill lines will start from positive charge, will end at the negative charge. Then this fill lines which has been cut out at this time t is equal to T by 4 will keep on propagating towards this direction. So now what we are showing here is only for two charges. There will be many charges and this process will continue for many charges. So you will have many fill lines. Those fill lines will be propagating out and that will create the electromagnetic waves. This is an intuitive and heuristic way of explanation of radiation from the Hertz dipole, and this gives you an idea how things are going on inside the Hertz dipole. But this is purely heuristic and intuitive way of explaining the radiation of Hertz dipole. And as you know that Hertz dipole is the basic building block for any kind of antennas. We can always construct all other antennas using the Hertz dipole. If you know how radiation is happening in Hertz dipole, then you can always do it for other antennas also. One more discussion we need to do is about the small antennas. How much small and up to what limit you can make any small antenna? Can you keep on decreasing the size of the antenna? So anyway, small size of the antenna is very attractive feature because you have many portable devices, mobile phones, tablet, all kind of devices, they have an antenna. If you have a small antenna, their size is going to become smaller and smaller, and it's a very attractive feature. So I mean, can you keep on reducing the size of the antenna? That's the question. Is there some limit, or I mean, you can keep on doing that, reducing the size of antenna? So basically, there is some limit to that. It's actually given by Chu-Harrington limit, and you will consider that now. So in order to do that, you consider an antenna and you enclose that antenna inside a smallest sphere. Assume that there is a sphere which can enclose this antenna, and that sphere is smallest in size, and the radius for this smallest sphere is a, let's say, r, let's say. In that case, there is some criteria you need to satisfy for the quality factor of the antenna. So you enclose any kind of antenna inside a sphere and assume that that sphere you are considering is the smallest sphere which will be able to enclose that antenna. So and consider the radius of the sphere is r. In that case, there is a criteria to be satisfied by the quality factor of the antenna, and the quality factor of the small antenna, actually for electrically small antenna, kr is less than 1. K is the free space wave number, r is the radius of the smallest sphere which is enclosing that antenna. So now the quality factor is given by 1 plus 2kr whole square divided by kr cube, 1 plus kr square into radiation efficiency of the antenna. So now this quality factor for the small antenna should be satisfied. For the electrically small antenna. So here what you can see is that you have a quality factor, you have also radiation, you have also size of the antenna. See, r will give you the size of the antennas because this is the smallest sphere which will be able to enclose that antenna. So this relation here is relation between the quality factor, size of the antenna, and radiation efficiency of the antenna. So this relation should be satisfied. So now this relation can be further simplified when kr is very much less than 1 for a linearly polarized antenna. If you have a linearly polarized antenna and kr is very much less than 1, then the minimum quality factor can be given by 1 by kr cube plus 1 by kr. So here minimum quality factor is related to the size of the antenna, and you know that quality factor is related to the fractional bandwidth of the antenna also. Fractional bandwidth of the antenna is 1 by quality factor. So from there, let's say quality factor is higher and higher, then fractional bandwidth will become smaller and smaller. So it's inversely proportional. So those things you need to worry, if you keep on reducing the size of the antenna. For example, if you keep on reducing the size of the r will become smaller and smaller, then this q will become larger and larger. So the minimum q you can have for any specific r is given by this q minimum. So now there's one more thing, is that antenna for any practical application should have a considerably high gain. If the gain is very low, then you won't be able to use the antenna. So whatever signal which has been radiated from the antenna won't be able to go for far away distance. It will die out very soon if gain is very low. So Harrington also give an upper limit of the gain of the small antenna. This is the maximum gain a small antenna can have, electrically small antenna can have, kr square plus 2kr. If r is very small, gain is definitely going to be small. If r is very small, quality factor is going to be very high. In that case, bandwidth is going to be very narrow because bandwidth is 1 by quality factor. So now let's take one simple example and see. Let's say if you have a Hertz dipole and size of the Hertz dipole is 0.01 lambda. This is an electrically small antenna. In that case, you find out q minimum. Q minimum is 32283. It has a very high q. That means fractional bandwidth will be very narrow. So fractional bandwidth for such kind of very small antenna of dimension 0.01 lambda is 0.00031. So it has a very narrow bandwidth. So one observation is that when you have a very high quality factor for a very small antenna, you have a very narrow bandwidth, and Second thing is that Herrington also gives you the maximum gain, and we have found out you can find out the maximum gain for this antenna, and it turns out to be 0.0638 or minus 2 dB. So this gain is very low, so you won't be able to use it for any practical applications. And in the above calculations, we have used that the sphere radius of the sphere with the radius of the smallest sphere which will be able to enclose this Hertz dipole of length 0.01 lambda is taken as 0.005 lambda. So now what you observe is quality factor is very high, bandwidth is very small, and gain is very minimal. No? So this kind of antenna, even if it is very small, you won't be able to use it for any practical use. So what you observe is that small antennas, even if size very small, then there is a trade-off. No? When the size is very small, quality factor becomes very high, bandwidth becomes very narrow, and you also see that from the relation first we have considered, the quality factor is also directly proportional to radiation efficiency. So all these parameters are interlinked. You don't have complete freedom of designing small antennas. You have to satisfy the Chu-Harrington criteria to design small antennas, and if you design a very small antenna, you see that there is no practical use for that. So you cannot keep on reducing the size of the antenna. There is some limit called Chu-Harrington limit. So nowadays, but people try to overcome all these limits in the performance of antennas by using many advanced technology like metamaterials. So basically, metamaterials are materials with exotic natural properties which are not available in the naturally occurring materials. Meta means beyond, materials, beyond materials, so beyond the naturally occurring materials. So this kind of materials has, your mu and epsilon negative. So metamaterials are widely used for improving the performance of antenna, and in recent years people are using EBG, electromagnetic band gap structures, to suppress the surface waves inside the material and to improve the antenna performance, efficiency, and gain. And nowadays people are also using the SSPP modes for designing antennas, which are called surface plasmon polyrethol. So SSPP modes are actually existing when you have a metal dielectric interface. So you have to do some kind of specific design in the antenna so that SSPP modes can be excited in the antennas, and it can be properly radiated into free space. So there is a lot of new technologies which are applied to the antennas to improve their performance. If you are interested, you can explore all these new technologies. There are many more technologies which will try to improve the antenna performance, and it will keep on coming in future also. Thank you. That's all for this class.